Hello, welcome back on a very wet, nasty day. The roads are an absolute mess. I wasn't even sure I was going to be able to get here on time. I had to exercise all my skills in using back roads to get here. Let's see, some administrative stuff. Homework number 5 is due today. Homework number 6, the last homework, is on Chapter 7, and the problems are as follows. 7.4 through and including 7.9 and 7.12. And they're due not. And the reason is that there just isn't enough time, so what we'll be doing is in fact giving out next week's solutions to those problems. So you don't need to turn them in, they won't be graded. Encourage you to do them before looking at the answers, because otherwise you don't get much benefit out of them. You get some benefit out of just looking at the answers, but more so if you try to do it yourself. So that's the last and final homework, coming down the home stretch here. The final. The final is a week from Tuesday. March 21st, which is the time assigned in the course schedule. We're not making any changes, 3:30 to 6:30. Now they've given us skilling, and there probably isn't enough room here for everyone and to assign alternate seats, so I'm going to look into seeing if we can get some of the overflow rooms and be able to spread people out. Any other administrative issues? Yeah.
When are the rest of the other homeworks going to be returned?
When they're graded, David says. They're in the pipeline.
Did homework 2 ever get graded? Cause
I'm sorry?
The homework 2, there was a mean put up, but I don't think they were ever returned. Is that correct? Or
we've never brought the homeworks to class to give back. They're all outside of Lily's office in ERL 444. So yeah, 1 through 3 have all been graded, and 4 is on its way.
Okay. Today we talk about I/O, and I brought in a bunch of toys to let you play with. Obviously the prototypical I/O device is a disk, so I brought some disks that can be taken apart and played with. This is sort of a typical disk of current vintage, 3-inch disk, and this one in fact only has 2 platters, but it has an actuator run by a stepping motor that moves the thing back and forth on a kind of rack and pinion gear down at the bottom. And this one has 4 heads, 2 platters, so it records and reads on both sides of both platters. The generation before that was the next larger size up, which were 5-inch disks. Let's see if I can open up this guy. And it's basically the same idea, although many of the disks of this generation and the next older generation, which were the 8-inch disks, instead of having stepping motors, had voice coil actuators, basically continuous pistons with electromagnetic coils around them to do the arm motion. This one is again a stepping motor that revolves this thing in small increments, and with a different kind of mechanical actuator moves the arm in and out. And again, this one also has 2 platters and records on 4 surfaces, so it has 4 heads. If you've never seen a disc before, it's probably worthwhile playing with it, and you can't do any damage to these, so at least not more than has already been done. Those are sort of conventional, and discs have been progressively getting smaller. The generation before the 5-inch discs were these, which are 14-inch discs, and in fact this is in pretty ready condition because it's been hanging on a nail in my garage for the last 12 years, but this used to have a bunch of my programs on it before the head crashed. One of the characteristics of these discs is that the head is in fact not in contact with the surface when it's reading and writing, when the disc is spinning. It's separated by an air gap which is very small. I forget the numbers, but it's micro inches. And if anything happens to disturb that air gap, like a particle of dust, which is big compared to the air gap, the head of the disc might dive because of the aerodynamics into the surface of the disc. And if it catches enough particles on the disk, it'll suddenly make a score mark all around the edge of the disk, which produces all sorts of particles which are now floating around this hermetically sealed disk, causing the rest of the heads to crash at the same time. So a head crash is usually a catastrophic event. In fact, this one I don't actually see the score mark that caused the head crash, but I was quite disappointed that I hadn't backed up my programs at the time that happened. Those are conventional I.O. devices. This is an example of one of the strangest I.O. devices I've ever seen. It's something that, of course, IBM made. It's called the Photo Chip Store, and I guess they made it in the mid-70s or something like that. And it was their idea of how to do, at the time, a very high-density, very capacious, but very slow mass storage device. And what it is a plastic cartridge that has bunches of these little plastic sheets, each one of which has been optically recorded once only. It's a write once, read many times disk with, I think, about 4 megabytes of information. And the machine was practically a photographic developer as well as an incredible mechanical contrivance, because there were hundreds of these little packages, each of which has 32 of these little plastic sheets, all in the machine at some point along conveyor belts or little pigeonholes and moving around from station to station. An elaborate mechanism both to write blank ones and to retrieve already written ones in order to bring them into a read station. So there would be a mechanical device that opened up this little cartridge and pulled out the particular sheet that it needed and put it into a reading station and then return it to its original spot. I think they made 3 of these machines. Each one of them required a dedicated technician full-time to keep it running because it was a mechanical nightmare. And as far as I know, one was in IBM, one was in Lawrence Livermore Labs, which always gets one of everything. And I don't know where the third one went. Needless to say, I would guess that they never recouped their engineering costs in developing that particular machine. I'll pass it around, but I just assume you don't open the cartridge because they'll spill all over the place. So I'll rubber band the one that I just extracted to the cartridge. So we're talking about I.O. and input-output, generally speaking, has been ignored in most computer courses. And essentially, we're doing exactly the same thing by relegating it to the end of the course and giving it 1 day's worth of talk. And, well, why is that? Well, for one thing, I think CPUs are just more fun. It's the sexy field. There's a symposium that goes on every year at Stanford called Hot Chips. It's been going on for almost a decade or something like that. And people finally realize that there is more to building computer systems than just the CPU chip. So, in fact, there is now an equivalent symposium held at the same time called Hot Interconnects to talk about I.O. or interconnection of processors, but it's only been recently that it's been getting that kind of academic attention. Part of it is that the CPUs are more academic-type problems. They're easier problems in a sense because the CPU is just a processor that has a bunch of memory on it and does computation. It reads bits from the memory and writes bits to the memory. I.O. is much more complicated because it interacts with messy mechanical devices like that. It interacts with human beings, which cause all kinds of problems in modeling of computer systems. And it's, in general, a much harder problem. But it's a bad thing to ignore it. It's not only unfair, I mean, it leads to misleading results, because in more and more, I.O. is going to have a significant effect on the total system performance and the total system cost, especially when what you're interested in is response time, how long it takes you to get your money out of the ATM machine, not in throughput, which is more a function of how much they have to spend to get the appropriate number of cycles and transactions per second in back of the ATM machine. The other thing is that I.O., to an increasing extent, is what differentiates different machines. Everybody is building processors, computers out of the same processors. Both small systems and large supercomputers are all getting built out of the same microprocessors, arranged in different ways. And the arrangement and the memory and the I.O. systems are what going to make the difference. And if people are going to still be able to hope to sell machines that cost $1 million, which is what keeps some companies in business, they have to do a lot for I.O. In order to make machines that are differentiated. IBM recognized that a long time ago. IBM for years in their mainframe systems put an extreme emphasis on getting high I/O performance, and they were uniformly recognized as the superior technology when it came to massive amounts of very large storage devices, including some that were successful, unlike the photo chips are, and getting high bandwidth in and out of the CPU. The applications that people are concentrating on are increasingly also using or emphasizing I/O performance, the multimedia applications where you expect to get lots of real-time performance out of a screen and audio and other gadgets require incredible bandwidth and response time in order to be realistic. There will still be a market for companies that build supercomputers, and if you're interested in high-performance processing for scientific calculations of the kind that the old supercomputers were used for, there's still a market for that, but as a fraction of the overall market for computing, it's diminishing. Predicting performance of a system, which includes CPU and I/O, as well as other components, is much more difficult, and that's part of what makes this, in general, a more difficult problem. A single program doesn't work anymore because most of the single programs, all of the benchmarks that we've been talking about, are unrealistic. They either don't do any I/O or they have no facility for doing CPU and I/O overlap. There aren't multiple programs and multiple I/O operations going on at the same time. In order to measure and predict system performance when you include I/O, we need much more complicated kinds of benchmarks, including those that do multi-programming and those that do online transaction processing, since that's the commercial application of large systems, which is most important. And we'll talk more about that in a little while. So in looking at performance, now we have two components. We used to have only the CPU time, and remember we kept hammering about the fact that the CPU time is the measure of the performance of a system. Well, now we have two pieces. We have CPU time and we have I/O time, and they come in little chunks. Sometimes the CPU isn't running because it's waiting for something to happen in the I/O to give it something useful to do, and vice versa. Sometimes the I/O isn't running because it's waiting for the CPU to do something, and the pattern of CPU and I/O interactivity and the amount of overlap at each particular piece is very complicated and depends on, in a very intimate way, on the details of what particular program you're running. But if we try to take the next level of abstraction and ignore the sequence in which CPU and I/O are independently interspersed over time, let's collect together all of the CPU time, collect together all of the I/O time, and then look at the amount of time which is overlapped, the amount of CPU time which also happens to have I/O activity going on in parallel. So then if you look at the total amount of time that it takes a particular job to occur, or a particular set of transactions to occur, it's the time of the CPU, it's the time the CPU had anything useful to do, plus the time of the I/O, minus the time of the overlap, the sum of all of these little pieces where the CPU and the I/O processing were overlapped. You've got to be a little careful here in measuring CPU time, because in some systems, especially older systems, the CPU is never not busy. And the CPU is doing something during this time when I've shown it as a blank. But if it's doing nothing that's useful, if it's just waiting for the I/O, then you can categorize that as non-CPU time because it could have been used for something else. Now the question is, given those two parts, what happens if you speed up one or the other of them? How much do you wind up speeding up the entire transaction? Well, let's look at speeding up only the CPU. Right? So we've got a certain amount of CPU time, we've got a certain amount of I/O time, and then a certain amount of the overlap time between them. Clearly the CPU time gets sped up by whatever factor we've sped up the CPU. If we make it go twice as fast, then we've decreased the CPU time to half its value. The question is, what happens to the overlap time? And there are several different models one can choose to estimate what is going to happen if we make the CPU faster. The real story is you don't know. And the only way you do know is to go back to sort of the original diagram and look in detail at the program and see which CPU cycles that are made faster will wind up being overlapped with I.O. and which won't. I'll show different ways of doing that calculation. Then, in fact, the overlap gets reduced by a factor of 2. It's proportional reduction. So the time for the workload is the reduction in the time of the CPU, and in addition, the overlap gets reduced by the same amount. Right? We haven't slid these two bars relative to one another by any way to increase the overlap or decrease the overlap. That's sort of the simple case. So if we take a look at an example, let's say that we originally had a workload that took 100 seconds in total. So that's that distance. And the CPU time was 80 seconds. The I.O. time was 30 seconds. And we speed up the CPU by a factor of 5. What happens? How fast have we sped up the total workload? Well, the overlap is the difference between the sum of the CPU time and the I.O. time, the 80 plus 30, minus the original workload time. So the overlap, this piece over here, is 10 seconds. So in terms of the original equation, the total time is the 80 seconds of CPU plus the 30 seconds of, the 80 seconds of CPU plus the 30 seconds of I.O. time, minus the 10 seconds of overlap to get the original 100 seconds. We now speed up the CPU by a factor of 5, so the CPU time speeds up by a factor of 5. The I.O. time is unchanged. The overlap decreases by that same factor, factor of 5, and the result is 44. So we sped up the CPU 5 times. We sped up the entire transaction processing by 2.2 times. You can do the same kind of calculation if you speed up only the I.O. Again, it's the original time of the CPU plus the time of the I.O. divided by the speed up minus the time of the overlap divided by the speed up of the I.O. If you're speeding up both of them, it gets a little more complicated. You certainly divide the CPU time by its speed up, the I.O. time by its speed up, but what do you divide the overlap time by? It's certainly not the sum of the speed ups. It's probably something. A reasonable assumption, if you want to do that, is something like, let me write that, is the new time for the workload is the time for the CPU over the speed up for the CPU plus the time for the I.O. divided by the speed up for the I.O. plus minus the time which was originally overlapped divided by the maximum of the speed up for the CPU and the speed up for the I.O. Now again, this is somewhat arbitrary because it represents a particular model of how you think, what's happening to that overlap, that it's shrinking by the maximum of how much the CPU shrunk and how much the I.O. shrunk. But in fact, it might be shrinking by nothing at all, or it might be shrinking more than the CPU or the I.O. is shrinking. So let's look at a couple of those other cases and see what can really be happening. This is what we had before. Let's say we have 3 units of I.O. activity and 3 units of CPU activity, and we overlap 1 unit of each. So the total transaction time is the I.O. time plus the CPU time minus that overlap. What we had just been doing before was saying, in the case where we're speeding up the CPU by a certain amount, that we're shrinking the CPU, and in this case it looks like we're shrinking it by about, 6, something like that, because it's half the size of one of these 3 boxes. And we're shrinking the overlap time by that same proportion. So we're making the new overlap time be 1/6 of the original overlap time. And that might be a reasonable assumption if your model is that as you're speeding up the CPU, you're sort of removing instructions, of these billion instructions that this represents. You remove them equally from the time which is overlapped and the time which is non-overlapped. That may not be the case. There are some places where The CPU, for example, may be doing something that's waiting for I.O., and no matter how much faster you make the CPU, it's going to take the same amount of time to do that. So that part of the CPU execution won't be sped up, and other parts will be sped up more. So here are the two sort of worst and best cases for what might happen when you actually do a speed up like this. One is that in the worst case, as the CPU is speeding up, you speed up, first of all of the parts of it which are in parallel with the I.O., and then you speed up the parts which are not in parallel with the I.O. And the result is total time, which in a picture like this is the total amount of original I.O. time plus whatever the CPU got reduced to, the CPU over the speed up. This factor is in here for the stranger cases. If you wind up not decreasing the CPU enough so that the overlap goes to 0, then this represents the amount of overlap that's left over because you couldn't quite get it to go to 0. The best case is when you start speeding up the parts of the CPU that are not overlapped, and then what you're left with is the I.O. time plus the CPU time over its speed up, and perhaps minus the CPU time over its speed up. If you've reduced it to the point where it's smaller than the original overlap, then you've hidden all of the CPU time. So these two factors cancel out, and you wind up with the total transaction time being exactly the original I.O. time. If you don't decrease the CPU by that much, then in fact you might not have used up all the overlap, you might still have some CPU time left over, and then you have to subtract the overlap. So these represent the best and worst cases of what can happen. Benchmarking for CPUs is not in a wonderful state because, as we saw, there are lots of ways of writing benchmarks that come up with misleading results. Benchmarking for I.O. is even in a worse state because it's much more complicated. There are more components. You now not only have to worry about the CPU and memory, but also channels, controllers, devices, and human beings. If you're looking at the total transactions per second time of a system, the book points this out, people have done studies that show that if a human being is in the loop and you're measuring how long it takes a computer system to execute a transaction, and then you add to that how long it takes the human being to do his thinking and prepare the next input. You know, you've made the next input to your text editor or something like that. To first approximation, you would think that making the CPU faster is not going to affect how fast the human being is running. But in fact, that's not true. People have done studies that show that the faster, within limits, the faster you make the computer work, the faster the human being works. I'm sure it's a psychological effect that your mind is less diverted, I suppose, or you sort of get into a pace with the machine, and the faster it goes, the faster it makes you go. But that makes doing a controlled benchmark a relatively difficult thing to do. Still interested in the standard kinds of measures. We're interested in the throughput. In some ways, the system people are interested in the throughput. They want to know how many bucks they have to spend for a machine that will provide the throughput that's necessary. And we're interested in the response time or the latency, which, as a user, how long it takes the machine to respond to your request or to do a particular transaction. Unfortunately, in many cases, these are related inversely to one another, and things you do to increase the throughput may reduce the latency and vice versa, especially when it's a complicated system that has queues. We don't talk any about queuing models in this class, but if you imagine a model of a transaction which has some I.O. going on, and in front of that I.O. device is a queue of requests waiting to do that I.O., and there's some CPU perhaps that's making those requests, and the requests eventually get filtered back. From the point of view of the requester, if you want to minimize latency, what you want to do is keep this queue as empty as possible. So as soon as he makes a request, then his request is at the top of the queue, it gets processed, and he gets his response back. So, you know, that's the best case for being online in the checkout for Safeway, right? You get up to the checkout and there's nobody in front of you, you get processed right away. From the throughput point of view, how many checkers are at Safeway twiddling their thumbs waiting for customers, it's not the best situation because, in fact, there are lots of cases where the queue is empty. So the throughput isn't great, the response time is great. So there are lots of strategies and architectures where increasing one decreases the other. Makes it more complicated to produce summary measures for the performance of a complicated system. If we look at the kind of benchmarks that people have done for I/O, there are three styles. There's the sort of supercomputer style, which is based on more measuring throughput than anything else. It's seeing how fast you can read and write large blocks of data into and out of memory from disks or I/O devices. If you're building supercomputers, that's interesting. If you're not, it's probably not. And something more interesting for building general-purpose servers is the file system I/O performance. In that case, throughput may not be the most critical issue because lots of the files that you access are small. I don't know what small is defined as here. It's probably 128 bytes or less, but some large number, like 80% of files that are accessed, are tiny. There are more reads than writes. But once you're within a file, large or small, the reads tend to be sequential. So the characteristics depend a lot on the characteristics of the applications that are being run. The other problem, too, is that any measure of file system performance is a composite of the measure of the hardware and its CPU and I/O systems and so forth, and the file system and what it's doing. And Unix file systems have their particular characteristics, and other file systems have very different characteristics. So again, it's hard to extract the components separately. If you're a bank, or if you're building computers to sell to a bank, then the kinds of things you're interested in are transaction processing. And a bunch of years ago, probably 10 or so, users of transaction-like systems put together a benchmark that tries to simulate that kind of load and measure its performance in terms of transactions per second. And a transaction is defined as something that takes 2 to 10 disk accesses. This may be an ATM teller access. Requires 2 to 10 accesses to a disk file, and very few instructions, 10,000 instructions or something like that, which is unrealistically low because it probably takes more than that even to schedule a disk operation in most operating systems. But one of the things they did for this benchmark to try to make it more realistic is sort of up the ante. Every time you try to make your transaction processing system report a higher number of transactions per second, you have to do that on a machine that has a larger disk. You have to scale the size of the disk and the number of entries along with the processing rate that you're reporting. Sort of makes it super linear, grows faster than linear. And we'll go through an example a little later that shows in detail how one might do a calculation like that. What they were trying to do was avoid small file sizes that could fit in the cache of a reasonable processor and get incredibly high transactions per second, which were unrealistic. The CPU may be getting faster, but the I/O system is not keeping pace. And they wanted something that scales so that they get the effect of both CPU and I/O and doesn't take advantage of little tricks. That's I/O in general, although we've been talking mostly about disks. Let's bore in specifically to disks. It's the prototypical I/O device used for two main functions. One is the virtual memory backing store. It's the level of a multi-level cache after the last semiconductor storage. And it's accessed with the cooperation of operating system software, but primarily under the direction of hardware that does the page table mapping of the kind we saw. And then there's file storage, which is an entirely different mechanism, at least from the application programmer's point of view, for accessing the same disk using the same operating system, but in an entirely different way. And in fact, from an application point of view, there are people who have argued about the distinctions between these two, and maybe all files, in fact, should look like virtual memory, and you never do file I/O operations. You just access big arrays, which you've defined to be mapped onto files that are actually residing on the disk. But in fact, there are these two very different ways of accessing disk storage. I'm sure you all know the basics of how disk works. They're floating around, so you've seen them. There are a bunch of these platters that are all revolving around a common spindle. There's an actuator arm that has heads on it, and all of the heads are positioned over an equivalent position on all of the platters at the same time. For each particular head, the data that it can access as the disk revolves is one track, and because there are 500 to 2,000 different positions for these heads, as the actuator arm moves in and out, there are 5,000 to 2,000 of these concentric tracks on each of the surfaces of each of the platters. And each of the tracks is then divided into sectors. Sectors are typically 512 bytes, but certainly have been different, and in particular older style mainframe disks, the sectors were variable size, and each sector had in front of it the size of the sector. And then the question is, how do you find a particular sector if they're all different sizes, and when you start reading from the disk, you don't know which sector you're at? And the answer is that for variable size sectors, they had ID fields, and in front of each sector was an ID, and in fact it could still be used, that identifies which sector number on this track this upcoming data is. They even got more complicated than that, and in the old IBM, the standard IBM mainframe disks, in fact, had three components to their sectors. They had the ID field that said which sector is coming up. They had a key field, which was an arbitrary string that was associated with this sector that the hardware could do an automatic search on, and then there was the data of variable length. And this arbitrary key, which was optional, was a way to have the hardware do some of the searching involved in doing database updates. If you're looking for a particular transaction record for somebody's social security number, you could give the disk an instruction that said, search all of your tracks in parallel for a record that has a key, which is some guy's social security number. And IBM's ISAM, Index Sequential Access Method file system, did that, and a lot of the transaction processing systems of the 60s and 70s were based on that architecture. It eventually fell apart because, in fact, that search goes incredibly slowly compared to the speed at which CPUs were going. That search goes at one track's worth of records per revolution, or maybe several if you've got all of the heads doing the searches at the same time. But still, this is mechanical revolution speed at 3,600 RPM, which is, what, 16 milliseconds or 18 milliseconds a revolution, which is incredibly slow compared to how fast the CPU could do the key search if it just read in all the keys in one big block and searched through them in CPU rather than in disk operations. So in fact, modern disks tend not to have any of that complication of keys. They tend also not to have the complication of variable length sectors. Sectors tend to be fixed size. It was traditionally the case that even as the circumference of the track increased, you didn't increase the amount of data that was stored on that track. So as you went further out toward the edge of the disk, the bits simply got farther and farther apart. And part of the reason for doing that in the case of fixed length sectors was to make the accounting easy, that you could always do a straightforward computation to determine where or which track a particular sector was going to be on. But that's a pretty fundamental waste of data storage, because there's no reason why you can't store as much data per linear inch on the outside track as you can on the inside track, which means you can get a lot more on the outside track. And in fact, more modern disks are moving to constant linear bit density, which gives you more sectors and more data on the outside tracks than the inside tracks. It comes in, unless you're changing the rotation rate of the disk, at a higher speed, so you've got to deal with that. You've also got to deal with the fact that it's more difficult now to compute where a particular sector is located based on its block number, because there are a variable number of blocks per track. A cylinder is the data accessible on all of the platters without arm motion. So it's the sum of this track and the bottom track and this track and the bottom track on that platter without moving the arm. And operating systems that try to maximize or minimize the latency in accessing records try, when possible, to allocate related records on a single cylinder. And notice this is a case where you again begin to mix what you would like to be a clean architecture from an operating system point of view with the details of how the hardware architecture is working. You now can't just give the disk controller an arbitrary block number because two adjacent block numbers might be on different cylinders, and you didn't realize that, and you wanted them to be accessed quickly together. So if you want to get the maximum performance out of one of these disks, you have to begin to propagate the configuration of the disk back up to higher levels of software, which is not such a wonderful thing to do. So how long does it take to access a record on a disk? Well, it's the sum of several components. One is that it takes a while for this arm to move over the appropriate cylinder, and that while might be 5 to 20 milliseconds on typical disks, 5 milliseconds especially on the smaller disks where the mass of the arm is not as much inertia, and I'll talk more about this in a second. There's the rotational latency. You've got to wait for the disk to spin around so that the record you want to read or write is underneath the head. Well, on the average, it's going to be half away. Sometimes it might be right there, and as soon as you start reading, you encounter it. Other times you might just have missed it, and it just passed by you, and you have to wait for almost a full revolution for it to come around again. And on the average, you're waiting for half of the rotation period of the disk, or about 8 milliseconds. Once you've found the record, you've got to do a transfer, and the transfers typically occur at some rate like 5 megabits per second. And then there are overheads, both in the controller, which might be 1 or 2 milliseconds, and in the CPU operating system overhead for scheduling the operation, which might be 1/10 of a millisecond or a millisecond. So if you're transferring a sector, which is 512 bytes, then it's going to take you, let's say, 10 milliseconds to do the seek, 8.3 milliseconds to wait for the rotational latency, 1/10 of a millisecond to actually do the transfer, and a millisecond or two for the controller and operating system overhead. So it's a total of about 20 milliseconds to read one sector, of which the transfer time was an absolutely negligible part. And I'll talk more about how one deals with that, but notice that if you're using this disk for virtual memory backing store and you're accessing these sectors in relatively random order to accommodate cache hits in the cache, the overhead is incredibly high. And that's part of the reason why for virtual memory we try to reduce the miss rate as much as possible. Okay, a couple of words about seek time. It's not as simple as it looks. There's certainly a minimum and a maximum, and the minimum seek time if you're actually doing a seek is a cylinder, and the maximum is all cylinders. But how do you compute the average seek time? And every disk manufacturer, when he tries to sell you a disk, will quote you a number for the average seek time, and chances are he won't tell you how he computed it. And there are lots of different ways of doing it. You can take the average of the minimum and the maximum. You can take the time to seek 1/3 the distance under the assumption that if you choose a random spot to start from and a random spot to end up at, that the average distance you will move is in fact 1/3 the maximum possible distance. You can look at all possible seek distances and average them. You can do benchmarking. You can do random reads or actually run a benchmark and compute what the average seek time is. These will all give different numbers, and you need to ask more questions if you are given an average seek time to understand how it's been computed. Interesting thing is that seek time is not necessarily a linear function of the distance. It depends on the mechanical stuff that goes into building it. For one thing, there's inertia in starting and stopping the mass. So seeking 10 cylinders might not be 10 times the cost of seeking one cylinder because you had to pay for that starting and stopping time. There also may be settle time. After the thing stops, everything is vibrating for a while, and you have to wait maybe a millisecond for all of that to stop so that you can reliably read the data that's passing by. For certain kinds of actuators, it tends to be, in fact, more like the square root of the number of cylinders, proportional to the square root of the number of cylinders, for those voice coil actuators I was talking about. But this is only an example. It's not necessarily the case. The book shows an interesting figure where, in fact, it's even non-monotonic. It could take you longer to seek to a shorter number of cylinders than the other way around. And some reasons for that might be that they have different strategies. They put different amount of power into the voice coil if they know they're going to go a long distance. And if they don't carefully control the breakpoints for where they increase power or decrease power, or sometimes they can't, then you wind up with these strange cases where it takes shorter time to seek longer distances. The other thing to watch out for is that many of the seeks, if you look at just accessing two adjacent blocks, might be zero distance. In fact, people have argued and used in a lot of these computations that 50% of the seeks are zero distance because of this kind of spatial locality that works out to be on the same cylinder. And sometimes disk manufacturers, in fact often, they will quote an average seek time assuming that 50% of the seeks didn't take any time at all. That's another way to fudge the numbers. Okay, so how do we make it go faster? If, in fact, this problem of access time is such a big one, what can we do? Well, one thing you can do is try to read from multiple heads at once. After all, you've got all of these heads on the platters over all of the data at the same time. Why don't you just read all of the bits from all of the disks and somehow squash them together to make one block? Well, there are disks that have done that. It has some problems because, in fact, there are both electrical and mechanical skews. The bits coming off one platter might be slightly delayed from the bits coming off another platter. And if you want to reassemble them in the correct order, you've got to be able to adjust for those differences in propagation time, those skew differences. You can make the problem a little bit better by interleaving not at the bit level, but at the byte level. You read one byte from each platter, or one block from each platter, and use buffering to present them back to the CPU in the appropriate order. That too has been done, and it increases throughput. It makes the controller more complicated, because now the controller has to do buffering. It incidentally still has a skew problem. It's not quite as serious, because you're not reassembling bits to make individual bytes, but you still have to reassemble bytes to make blocks, or blocks to make larger transfers, and to get that happening in the correct order. There are lots of things that the software can do to increase the throughput. For one, it can use big blocks and do multiple transfers of either big sectors if that's available, or consecutive sectors, under the assumption that consecutive sectors are consecutive on the tracks and get accessed without an additional latency. So it can use big blocks. It can optimize the placement on the disk, keeping things that are going to be used together on the same cylinder, if possible. It can also punt the problem altogether and, in fact, put a big cache in front of the disk as used for file I/O. Now remember, there are these two different styles of using a disk. One is as a second level of or nth level of a cache for a virtual memory system, in which case you probably wouldn't want to have yet another cache in main memory for it. But if you're using the disk for a file system, then it makes eminent sense to use some main memory as a cache for the blocks of the file system that are on the disk. And in fact, when you add your next 24 or 16 megabytes of memory to your Sun system, probably a lot of that storage gets used for a cache in front of the file system access as a way to make the machine go faster rather than anything else, rather than giving you more physical memory for your virtual memory system. Another way that people have talked about increasing the throughput and getting certain other benefits is to use more than one disk, more than one sets of platters, more physical spindles than a single one, and try somehow to get them all acting together as a single high-performance logical disk. So you spread the data over many disks. That's called data striping, and we'll look at several different ways to make that work. One of the things you've got to watch out for, though, is that it has a serious side effect in most cases, which is decreasing reliability. If the mean time between failure of a particular disk is 200,000 hours, something like 23 years, just a little optimistic, but not that much, actually. Disks are incredibly reliable. And if you have an array of 100 disks, and you need every one of those disks to be running in order to be able to run your computer system, then you've reduced the mean time between failure to something like 2,000 hours by a factor of 100, which makes an enormous difference. If you're using 100 disks, but you're not using them for these data striping, and one of them breaks, you can, the chances are you can continue to use your computer system. You know, some poor user's got his data out on that 100th disk that just broke, but the rest of the 99 users are still happy. So you don't count that as a total system failure. Calculating, by the way, mean time between failure numbers and understanding what it is they apply to, components versus systems, is an art in the science in itself. And if you're interested in learning a lot about that, you can make yourself very valuable to the computer industry because they worry about that stuff a lot. One way of getting around this problem of decreasing reliability as we add disks to gain performance is to add redundancy, to add multiple copies of the data strategically placed so that if one of these 100 disks breaks, our entire system isn't down. We can still continue to operate. And these are the so-called RAID, redundant array of inexpensive disks. And they're starting to be used in more and more expensive systems, and to compensate for the use of the word inexpensive, because some of these disks can be real expensive, you can also consider this to be redundant array of independent disks. Your choice. There are lots of different ways of doing this. The granularity of the interleaving, you know, how it is you data stripe. Do you put 1 bit of a byte on each disk, or do you put 1 byte of a block on each disk? Or do you put 1 block of a file on each disk? These are all valid ways of deciding to use multiple disks. And we'll look at several of the probably 24 different schemes that people have proposed and even sometimes built for doing this. The other thing you get to choose is where you want to put the redundant information. And we'll see that. This is relatively new. It was done by half of the authors of your textbook and some other people as well, of course. But it's all within the last 10 years, and it's all a result of being able to buy disks that are, in fact, relatively inexpensive. So you can think of putting 50 or 100 of them, or even 10 of them on a relatively inexpensive processor. Back in the old days, in the days of that photo chip store, a disk was an enormous box like a washing machine and typically cost $100,000 or $200,000. And in fact, they were sometimes very much like washing machines. The original disks that I used were had hydraulic actuators for the arms, and the arms were massive. So every time the disk would seek, especially from one end of the disk to the other, the entire disk would shake. And it was always our speculation that if we had appropriately oiled the wheels on these disks and run a program which would hit the resonant frequency of the cabinet of the disk, that we could actually get the disk to move across the floor and attack the operator. But we were never successful in getting that to happen. But they were impressive devices. They also had oil leaks because they were hydraulic. So half the time when the technician would come to fix the disk, he would bring a mop with him to mop up all of the oil that had leaked in the pan on the bottom of the disk. Okay, RAID, redundant arrays of inexpensive disks. Level 0 is the multiple disk use, but not redundant at all. In fact, this is level 0. These Ds you can think of as blocks of a disk file. So you spread the first 4 blocks across the first 4 disks and then begin repeating disks. You get great throughput because, in fact, you can give each of these disks a request to read a block at the same time. So you're reading 4 blocks of your file simultaneously, and you quadruple the performance. In fact, it doesn't have the best read performance in terms of latency compared to some of the redundant cases, but it has the best write performance, because anytime you want to write a part of this file, its data appears in only one place, and you just write the data. Right? But it has the worst reliability because of that. If any disk dies, then the entire file is dead, because a quarter of its data is now inaccessible. The next level up of simplification allows you to get some redundant information. You simply divide the disks in two, and whatever you write on the first pair of disks, you also write on the second pair of disks. So you've half the capacity. You've probably not increased the write performance because you can write block 0 on disk 0 and block 0 on disk 2 at the same time. You might, if you're clever, actually have made the read latency decrease, because these disks are all spinning at independent rates and in fact may be located over different cylinders. And if you know about that and can take advantage of it, then you can schedule the read from the disk which is going to have the minimum latency. The IBM mainframe disks were great for doing that, in fact, because they kept track of where they were at any given time as the disk was rotating. And you could read a register out. This is called rotational positional sensing. You could read a register out of the controller that said where it currently is in its spinning cycle. And if you had two disks, you could then choose the disks which would have the minimum latency for reading that block. People tend not to use this primarily because it halves the capacity, and that's just too great a performance, too great a cost penalty to endure. The next level up is taking a tip from error-correcting memories, and we never talked about this in this class. I assume you've seen it elsewhere. The basic idea is to take a bunch of bits, and in this case, let's look at the case where we're taking, for a particular byte, bit 0, bit 1, bit 2, and bit 3 of a byte, and writing it on 3 different disks. And then you write on some number of other disks enough information that enables you to, number 1, detect whether any of these bits is wrong, and number 2, to be able to correct it. And this is a Hamming-style code where each one of these bits represents an exclusive OR of some of the other bits, including the Hamming check bits themselves. The problem is it takes a fair number of extra disks to do this. The basic rule is that these 3 bits, when looked at as a binary number, after all, those 3 bits represent a binary number in the range from 0 to 7, there have to be enough bits there to be able to identify any one of these other bits, including themselves, that might be bad, and the case where none of them is bad. So this is sort of the maxed out case, where you can check 4 data bits with 3 redundant bits, and nothing is left over. Because if any one of them is wrong, then you could encode that with these redundant bits as 1 through 7, and if none of them is wrong, then you get a 0. And in general, it takes something like log of the number of disks of redundant information. Now, in memories, this is used all the time. And people are, in fact, willing to pay this price, which in this case is 3 out of 7. Obviously, as the word gets bigger, it's not that bad. But for memories, people are certainly willing to pay that price for getting an error-correcting code. People never do this for disks, and the reason is that you don't need to. Each of these is an independent disk. Each of these disks is recording its data collected together in sectors, and each of those sectors has for itself a check byte or an error-correcting code that enables the disk to independently know whether its bit is bad as a contribution to the total word. So this is a waste of time. And instead, you can go back to a much simpler scheme of having only a single disk. And that single disk records the parity of all of the bits that it's checking for. So now, under the assumption that each disk can tell you whether its bit is bad or not, the parity will be able to tell you what that bit should be. So if you read disk 0, 1, and 3 OK, disk 2 reports to you that it's got an error. It doesn't know, in reading its block, it doesn't know what its bit was. You can use the parity to compute what that bit must have been to get the appropriate parity bit. So it's a much simpler scheme, requires much less redundant information, and in fact has great bandwidth because all of the disks deliver their information in parallel. People in fact have built this kind of RAID. It's great for transferring images and things which you really need an incredibly high data streaming rate for, yet you want to be able to recover from the failure of any particular disk. So that's level 3. Level 4 is basically the same kind of thing, except it stripes at a different level of granularity. Instead of storing an individual bit on each disk, you store an individual data block on each bit, on each disk. And what you store on the parity disk is a block, same size as these blocks, which represents the exclusive OR of all of these blocks together. It's the parity bit for the entire block. It's basically the same picture, just a different representation for the striping. You read all of the bits for a particular sector from one disk before moving on to the next disk. The advantage of that is that small read requests, if you're reading only a single sector, only need to access one disk, instead of having to access all disks and getting all of the arms in motion at the same time, and keeping all the disks busy at the same time. That's okay if you're going to read big, long transfers, but if you're doing small things, you're better off accessing one disk that allows you to get multiple requests executing at the same time. The other interesting side effect is that when you're updating a block, in the previous case where you were updating a block, you had to update all of the disks plus the parity disk. In this case, if you're updating a block, you just update the single block plus the parity on the parity disk. In order to be able to do this, though, you've got to do a read modified write cycle. So when you're updating this block, you write the new data, and then you read the old parity and write back the parity which has changed because of the new data. You could equivalently read the old data and write it back and then just write the parity. No, I'm sorry, that doesn't work. You can't do that. You have to write the old data and then read and write the parity bits. One of the problems with this configuration, which gets used but not quite as much as the next one, is that the parity disk is a bottleneck. Yes, you can be doing multiple operations in parallel, but all of those operations are going to have to be reading the parity disk if something goes wrong. The more common case is, in fact, they're writing. And if you're updating this block and this block and this block with 3 different processes, for example, then all 3 of those processes have to be reading the parity blocks in order to be able to be updating them. The way to get around that is what results in the most common kind of redundant disk array. It's the same kind of thing, but now we have distributed the parity blocks among all of the disks rather than keeping it on a dedicated disk. It has 2 advantages. One is that it's not a bottleneck for multiple simultaneous writes, because chances are, or at least in a high percentage of the cases, different processes updating different data will be accessing different disks to update the parity blocks. And the other thing is that if you're doing reads instead of writes, then in fact now you can get 5 simultaneous reads going simultaneously if you happen to be lucky enough to get them distributed across the 5 different disks. In the case where there was a dedicated parity disk, that was never the case. You could never get 5 simultaneous reads. So this tends to be very popular. There are lots of nuances here. Notice, for example, this particular pattern of referencing the data. The 0, 1, 2, 3 across the top row. Don't start D4 over here. Start D4 over here. And then 5, 6, 7, 8. 5, 6, 7. And then 8 over here. Basically, the idea is that as you're reading sequential blocks, you try to make uniform the access to all the disks so that you access all of the disks before you access any disk the second time. That allows you to get them pipelined. It allows you to get more consistent throughput of the disks. It's handy when you can do anticipatory seeks. If you know that 4 block cycles later you're going to be accessing disk 5, you can get disk 5 seeking toward its location while you're still off doing disk 4 accesses. So in general, it can tend to increase the overall throughput. Questions about that? Reads are becoming more and more popular. Slight change in subject here. One of the things we need to be able to do is to be a little quantitative in trying to analyze the performance of an overall CPU I/O configuration. And a lot of these problems are fairly simple. A lot of them are common sense kinds of calculations with a little bit of dimensional analysis thrown in. The book goes through several of them. I'm going to go through one of them here just to make you feel comfortable with your ability to do this kind of reasoning. The main problem in reading these, in doing these problems, the main difficulty is often just trying to understand what it means and keeping track of all of the bits and pieces of information, and then attacking it in small pieces, one at a time, to solve subproblems. It's no different than the general problem solving that you've used in the past. Let's say that we are building a multiprocessor. We're going to be using it for transaction processing, and we're going to be using this TP1 benchmark, which has this strange property that the faster the transaction rate, the more disk stuff you need. So let's make the assumption that each transaction that we are going to process requires 2 disk accesses to a 128-byte sector and 320,000 instructions on some CPU to which that disk is attached. And these disk accesses must be done on the disk that has that transaction file, that account file for that particular customer. And because of the way we've buggered the benchmark, we have to require that that account file will grow with the rate at which we execute transactions. And that growth is that the total account file size on that disk has to be 10 to the 7th times the number of transactions per second that that disk is going to be providing to us. This is a cost-performance analysis, so we have to know how much things cost. The base hardware, assuming you haven't added any CPUs yet, is going to cost you $40,000. That's for disk controllers and power supplies and cabinets and all of that kind of stuff. Each CPU that you choose to add will cost you $30,000, and for that you will be buying 40 MIPS. And we're going to use that in calculating, based on this 320,000 instructions per transaction, how many transactions the CPU can do. Each processor can have as many disks as you like. Eventually you're going to run out of instructions, but you don't run out of disk controllers. You can put as many disks on as you like. The disk controllers themselves have 2 millisecond delay, or the disk controller, depending on how many you choose. And you get a choice between 2 different disks. You get to choose an expensive $2,000 disk with a half a gigabyte on it, which is fast, and a fast transfer rate, or a less expensive, smaller disk with a quarter of the capacity, somewhat larger seek time, and a slower transfer rate. But it costs you less. So given all of this information, design the system for the highest transaction processing rate, assuming that you or your customer has a budget of $400,000. That's the statement of the problem. Anybody? Any questions on the ground rules? Yeah.
The transfer rate there, is that 4 megabytes and 2 millibytes, or is that?
No, that's I slipped on the shift key. That's 4 megabytes per second.
So why is the transfer rate slower even though the rotational speed is faster?
It's a good question. Maybe it has lower linear density of bits per inch on the track. It's a cheaper disk, by the way, after all, has lower capacity. That might tend to be unrealistic. In fact, as the areal density of metal oxide tends to be constant, and as you increase the rotation speed, you would in fact expect the transfer rate to increase. So this is not entirely a realistic problem. On the other hand, it has solutions that are nice even numbers. So that's important, not in real life, but in classroom situations. Well, the first thing we should do is to decide which disk we can use, because we can independently calculate how many transactions per second each disk is capable of sustaining, and then based on the price of the disk, figure out which one is a better deal. The access time for each disk is the seek time, plus the rotational delay, plus the transfer time, plus the controller time. So the seek time is either 8 or 12 milliseconds. The rotational delay is half of either a 5400 RPM rotational time or 7200 RPM rotational time. The transfer time is the time for 128 bytes based on either 4 megabits per second or 2 megabits per second, and the controller time is a constant 2 milliseconds. So it's trivial stuff as long as you watch the dimensional analysis and make sure that you've got everything in the denominator and the numerator correctly. And we see that it takes the big disk 15 milliseconds and the little disk 18 milliseconds to do a transaction. We know that it needs 2 accesses per transaction. So if we take the reciprocal of these and multiply by 2, or divide by 2, we can see that the big disk does 32 transactions per second, the little disk does 27 transactions per second. But we've got this other constraint, that the file size on each disk has to be big enough based on the number of transactions per second. The big disk, we've got 32 transactions per second. The file size has to be that times 10 to the 7th. That's 320 megabytes, which happens to fit on the disk. So this disk is limited by how fast its transfer rate is. We couldn't get any more TPS because it doesn't go any faster, not because you can't fit the file. On the small disk, it's the other way around. At 27 transactions per second, you would need an account file size which is 274 megabytes. Its capacity is only 250 megabytes, so this disk is limited by its capacity, not by its I/O performance. So it can only sustain 25 transactions per second, 250 megabytes divided by 10 to the 7th. So which one is a better deal? Well, if you look at dollars per transactions per second for the big disk, it's $2,000 over 32, or $62.50 per transactions per second. And for the small disk, it's $1,200 over 25, or $48 per transactions per second. And obviously smaller dollars are better, so in fact we make the choice that for all of the disks on the system, we're going to pick the smaller disk.
Question.
Yeah.
Does the 5400 RPM means 5400 rotation per minute?
Right. 5400 rotations per minute.
Don't you need to convert it to microseconds?
Yes. I mean, you need to do that conversion, and I have not shown the details of that here. Right, 54, I forget what it is, but it's, yes, you have to convert that to milliseconds or microseconds or seconds. You've got to work out the units and all of these things so they're the same. This is 2 megabytes per second, by the way. It's not something per millisecond, and my answer is in milliseconds. So you've got to watch the units as you go through and multiply and divide by the appropriate factors to make that all work out. I'm assuming you know how to do that. Okay, that's half the problem. We know what disks to use. We don't know how many, but we know what disks to use. Now let's look at CPUs and how many of those and how many disks. For each CPU, we were told that it's a 40 MIPS processor. We're told that each transaction takes 320,000 instructions. So that says that the limit for each CPU is 125 transactions per second. We want to add to each CPU the maximum number of disks we can to keep them fully busy. The disks from the previous page can do 25 transactions per second per disk. Dividing that into 125 says that 5 disks per CPU is a perfect match. The disks will be fully busy, the CPU will be fully busy. So now we know that we need an assembly of n CPUs and 5 n disks, 5 disks to each CPU, and the total system cost should be $400,000. So we know all the numbers. $40,000 for the base cost, $30,000 per CPU, $1,200 for each of the 5 n disks, 5 per CPU. It's got to equal $40,000. And Mirabile dictu, it comes out to an even number of 10.000 CPUs. So the solution to this problem is your customer should buy 10 CPUs, 50 2.4-inch disks. He will have a total account file size of 12.5 gigabytes, 50 times the 250 megabytes of each disk fully utilized, and he'll be delivering 1,250 transactions per second to his customers. These numbers are not entirely unreasonable. I mean, there are some minor parts that are unreasonable, but the interesting thing is that this seems to me to be a fairly low number. If you look at the number of transactions that Pacific Gas and Electric this afternoon is trying to process based on people reporting power outages, it's probably not this high, but it's a very large number. For big transaction processing systems, this is a relatively small number, and that explains why in some ways mainframes aren't dying as fast as people expected, because even for multiprocessor, microprocessor implementations, it requires big systems to get relatively modest transaction processing rates. Big iron may be dead, but it's dying more slowly than people expected, and it's getting replaced by equivalent big iron built out of lots and lots of disks and smaller microprocessors. I think we're about out of time. We will stop there. Next week is Dead Week. Back in the old days, Dead Week used to really be dead, and there weren't any classes, and we would all party. I mean, study for exams and finish our projects and so forth. But these days, lectures continue. So next week, we're going to finish up I/O, and then we'll move on to some other interesting topics having to do with multiple processors and caches and distributed systems. See you then.